Okay, let's get started. We have a lot we have to talk about today. So make sure you lock in because here we go. All right. So we just talked about Diels-Alder dienophiles. Now we have to talk about the dienes. So with dienophiles, we want electron withdrawing groups. In order to make those more reactive, we're going to find that for the dienes, we want electron donating groups. Okay, so butadiene, usually the way we draw it is as the S-cis conformation. Because that's what's going to react in the Diels-Alder reaction. But we can also have this sort of S-trans isomer. Now, these aren't like normal cis and trans, because we have free rotation around this single bond right here, and so they can go back and forth between either of the two conformations. And most dienes can do that. Of course, there's some, and we'll certainly see those that cannot. So S-cis is required for the Diels-Alder reaction. So, for example, if we have that diene and we try to react it with whatever a dienophile, even if we heat it, even if we have I don't know, an electron withdrawing group on the diene, we're not going to get a reaction. And the reason for that is this diene is locked in the S-trans conformation. So because it's in a ring, it cannot rotate to get into that S-cis position that it needs to be in order to do the Diels-Alder reaction. And in fact, if you were to try to draw this mechanism, you'll find that you can't. It's never going to look nice. And the Diels-Alder reaction mechanism should look nice. It needs to be a cyclic transition state. It needs to, the electrons go around in a ring. And you can't get that with this molecule. However, if you use cyclopentadiene, which, by the way, is a very common diene for the Diels-Alder reaction, this is locked in S-cis configuration, right? And so this looks more like the dienes that we're used to seeing for Diels-Alder reactions. And so if we do this reaction, it's really fast, and we get this bicyclic ringing system that looks kind of like that. Yes?
Can you just slow down a little bit?
Sure.
Sorry. I'm trying to like comprehend and iterate and stuff. Is that what it looks like?
Yeah, so one thing you can do with, because unfortunately, we're gonna have to start drawing a lot of those today. So one thing you can do to make that easier is start just by drawing the bonds that are broken and formed. Like that. And then what you'll get is that shape. Then we've got the part of the dienophile, and so these are drawn kind of in the same in the same positions and stuff that they are in the starting materials. And then we can draw that bond and that bond. Those are the ones that form in the reaction, and then our double bond. Yes?
Can you explain what the product is after the arrow again?
This one? Yeah, so so let's go to this one first, because if we draw out, the bonds that form between the end of the diene, each end of the diene and each end of the dienophile, we can draw our arrows, and what we get is this kind of thing, where we've still got the 5-membered ring from the starting material, and there's the dienophile right there. So we formed this bond and this bond. So we've got 2 rings now. And one of the ways that we can draw this is to kind of take it and rotate it like that, so that we're looking at it from the side. And then I'll see if I can make this look a little bit nicer. So right there is the 5-membered ring. So this carbon at the top here is this one. I'm drawing these on wedges to make them look like they're coming out towards you. And then the double bond goes there. And then we need to add these 2 carbons on the right, so we tend to put them kind of down there like that. So we're kind of looking at it from the side. Does that make a little bit sense?
What does very fast
So for this diene, where it's in the S trans conformation, so where it's it can't curl into this C shape. If you try and react that with ethylene, even if you heat it, you don't get a reaction. But if you use this starting material, where the shape of the diene is locked in that C shape because it's a ring, if we try and do that same reaction with this material, it happens very quickly, rather than no reaction at all. Okay, so for dienophiles, electron withdrawing groups increase the reactivity. For dienes, electron donating groups increase reactivity. So an example of that would be a methoxy group. So that is one way to increase the reactivity of a diene.
What is MEO?
MEO is methoxy, so we can write it as MEO or OME if it's on the other side of the molecule, and that is just R and then an oxygen and then a CH3 or a methyl group. Okay, so I think last time we talked a little bit about stereoselectivity in the Diels-Alder reaction. So when we've got a dienophile that's cis, the alkene is cis, then we get retention of that stereochemistry in the product. So both of those X groups are on the same side of the molecule. And then when we have a trans alkene, the same is true. We keep that stereochemistry, and so the X's are on opposite sides of the molecule. So that's stereochemistry. That has to do with whether the orientation of the molecule, of the atoms in space on the molecule. But regioselectivity is looking at which atoms are connected to which atoms. And that'll be a little more clear here in a minute. But if either the diene or the dienophile is symmetrical, as has been the case in all of these examples that we've looked at, right? So in this case, they both have a line of symmetry. It goes through them. If that's the case, only one regiochemical outcome is possible. So that means that if we take that molecule and react it with this one, so the diene with the methoxy group is not symmetrical. It's got a methoxy group on one of the sort of inner carbons of the diene, but not on the other. And then we react it with this dienophile, which is symmetrical. It's got the same thing on both sides. Then our option of which carbon to connect to which carbon versus, say, flipping it kind of upside down like this. It doesn't matter because we've got symmetry here, so there's always going to be a CHO group or an aldehyde on that carbon in the product, and there's always going to be one on the other carbon. So our product will always look like this.
Why is it the dashed lines instead of like the triangle?
Because I wanted to do it that way. As long as they're the same, when you have a cis alkene here, it doesn't matter if they're going away from you or coming toward you.
Okay, so if we did that on an exam, did it either way?
Perfectly fine. I'd been doing it on wedges every single time, and I figured I should do it the other way to show you that that was also legit. So if both of the reactants are not symmetrical, there's a different way to draw the methoxy group, just an oxygen with a methyl group hanging off. But now let's say that the dienophile is also not symmetrical. So now we have to make a choice. We could keep everything in this same sort of arrangement, which is a completely arbitrary arrangement that we've just chosen to draw the starting materials in. And we could say, all right, so we've got our methoxy group there, and then, well, I've drawn the aldehyde on the top, so let's keep it there. Okay, that's one possible product. But we could also say, okay, these molecules are just floating around in space, or probably in solution. What happens if we take the aldehyde and just flip it upside down, so that instead we have the CHO group on the bottom? If we do that reaction, then the aldehyde is going to end up down here. So I will just tell you that this is the major product of the reaction, and that's the minor product. I would say right now it's not really clear why that's the case. Like you would think that, okay, well, it probably doesn't really matter what position they come together in. The mechanism is the same regardless. But there is a method we can use to figure out which one is going to be the major product. So the rationalization we're going to use is how charges are distributed in the starting materials, specifically in the resonance structures. So we got to draw some more resonance structures. Okay. So there is our diene. In the diene, we've got our oxygen atom with its lone pairs. We also know that the methoxy group is an electron donating group. That's one thing we use to increase the reactivity of the dienes. And so one thing that electron donating groups do, surprise, surprise, is donate electrons. So let's draw that happening. So we can take these electrons on the oxygen, move them down to form a double bond. And then let's take the pi electrons from that double bond and move them onto that carbon at the end. So if we follow those instructions, doing resonance structures, one thing I like to do first before you start trying to figure out where bonds and lone pairs and charges go is just draw the skeleton. with just single bonds. And then you can figure out where everything else is going to go. Yes?
I'm confused. So why did the bond that went to the carbon above end up down below?
Why did...
Like on your stuff, you have like your lone pairs, right?
Yeah.
That went over.
Mm-hmm.
I thought that. I'm confused how that happened.
So if it looks like I'm just kind of pulling this out of nowhere, it's because I kind of am.
Okay.
And the reason I picked this particular resonance structure is because it's going to put a charge on one of our dying carbons.
I think I'm just confused. Where did the double bonds? Like on the little L that comes at the bottom. Why did that?
Here?
Yeah. Where did
Yes.
this bond go? Because we don't see it moving anywhere, and then you're just there and say, oh.
I haven't finished drawing the structure yet.
Oh,
Yeah, he said that's some skeleton. Which I draw first that you can then put.
Yeah. So yes, that bond is going to remain there.
Yeah, that's all. Okay.
Yeah.
I was like, where's it going?
Yep. Okay. So additionally, we've got electrons moving down to here, so that's going to become a double bond. Because of that oxygen is going to have a positive charge. And we've also moved this pi bond onto that carbon atom, so that means we're going to have a lone pair there. And that carbon's going to have a negative charge. So there's a resonance structure for that starting material. You could draw other resonance structures if you wanted to. I've picked this one because it puts a negative charge on one of the carbon atoms that was originally part, well, it's not originally part of the dying, it is part of the dying. Yes?
With the negative charge of the lone pair, why does it not become just like another line instead of a lone pair?
Because those electrons used to be between these two carbons, and now they're just on that carbon.
Okay,
Yeah.
that makes sense. Thank you.
So this resonance structure tells us that the dying is electron rich. So why is that the case? Well, the dying is these four carbons right here, sort of the actual functional part of the dying. And when we draw this resonance structure, or really when we draw any other resonance structure of this molecule, we're going to end up with more electron density, more lone pairs, more negative charge on these atoms. Okay, let me do the dienophile, and then I think you might see what we're doing here. Okay, so the dienophile is this, but CHO we should probably draw out more explicitly as that. So the C is this carbon in the middle, then the H on the end, and then the oxygen is double bonded. So CHO is an aldehyde. Okay, aldehydes are electron withdrawing groups. So as the name suggests, we're going to try and withdraw electrons away from the dienophile double bond. And if you remember, I don't know, it might have been the first resonance structure you ever drew. I think it was for me, but when you've got a ketone like this of any kind, a carbonyl, we can move the pi bond up onto the oxygen. By the way, the oxygen has two lone pairs. And additionally, we can have this double bond, or the pi bond rather, move over and instead be between these two carbons. So why are we doing that? Well, let's look at the product of that resonance. I'm going to draw it out fully so Maddie doesn't freak out.
I think I was trying to listen and draw, and then I was like,
Okay. So I followed the instruction, right? Did I do it? Yes, I did it correctly. Okay. I followed the instructions. No, I didn't because I forgot a charge. Look at me. And that's the important one. So I followed the instructions here. I've moved this pi bond over to be right there, and this carbon is left without its 8 electrons that it wants, so it's going to have a positive charge. And then with the carbonyl, we've moved the pi electrons of the carbonyl up onto the oxygen. So now we've got a single bond there, 3 lone pairs, and that will have a negative charge. Okay, so that's our resonance structure for this guy. And the dienophile is electron poor because of this resonance structure, because we've pulled some electron density away from the dienophile double bond and toward the oxygen. And so that makes this area of the molecule electron poor. All of the examples I'll give you look pretty much just like this. Because this is a really common case for this sort of thing. So we know from playing with kids' toys that opposites attract, like magnets. And so, well, that's good. We've got an electron-rich diene and an electron-poor dienophile. I think this is good news for having a reaction occurring. And so what we're going to do is look at these resonance structures just at the part that is like the critical part of the diene and the dienophile. And that will be more clear if I redraw our reaction. So that's the important part of the diene, where you draw the mechanism. And so we see that that carbon up there in that resonance structure, it has a negative charge. It has a formal negative charge. And so when the molecule exists, either in gas or in solution, the actual structure really is sort of an average of all the resonance structures you can draw. And so that tells us that we have at least some sort of partial negative charge on that carbon. Do we remember that notation, the delta? That just means partial charge. Okay. In the same way, we can look at the aldehyde and say, all right, in our resonance structure, we have a formal positive charge right there. And that means that in the actual structure of the molecule, we at least have a partial positive charge on that carbon. So we can put a partial positive charge there. Now, you'll notice I haven't drawn it here yet, and that's because we have to figure out which way we're going to put it. Are we going to draw it with the aldehyde at the top and the partial positive charge at the bottom, or do we want to flip it upside down? So, if opposites attract, and we've got opposite partial charges on this carbon and this carbon, let's put them as close together as we can. So, that means that the carbon with the partial positive charge is also going to go on top, and that means that the aldehyde is going to go on the bottom. Okay. Now, when we form our bonds, we just do this the same way that we have always been doing it. And now, we've got our methoxy group there. And as I said, for the major product, we've got the aldehyde down at the bottom. Okay, so technically, you need to do this every time you're predicting the products of a Diels-Alder reaction where we have two unsymmetrical starting materials. But in practice, you'll notice there's a trend here. So in the diene, we have an electron donating group. So let me... It's an electron donating group. And when we've got our electron donating group, that means we're going to end up with a negative charge, or at least a partial negative charge, on the side of the diene that's closest to the electron donating group. So kind of this top half of the diene where we've got the electron donating group, that's where we're going to have our delta minus. In the same way, that aldehyde is an electron withdrawing group, and that means we're going to have a delta minus, a delta plus, partial positive charge on the side of the dienophile that's further away from the aldehyde. Okay, what does that translate to? Well, that tells us that usually, if you've got a diene with an electron donating group and a dienophile with an electron withdrawing group, they're usually going to end up as far away from each other as possible.
Do they ever go near each other?
No, the problem is you don't always have an electron donating group and an electron withdrawing group in the right places. In examples I'm going to give you, they will be in the right places. All right, I'm going to give you an example. And just work on that when you get a chance. Okay, when we introduced, rather, pericyclic reactions, we had this little table that told us how many bonds were broken and formed in cycloadditions, electrocyclizations, and sigmatropic rearrangements. That's not good for today because I'm going to say that word a lot for the rest of the class. Anyway, Diels-Alder is cycloaddition. So we add 2 sigma bonds that break 2 pi bonds. Electrocyclizations, we're going to skip talking about those in detail, but we are going to talk about sigmatropic rearrangements. And so we have no net change in the number and type of bonds in the molecule in a sigmatropic rearrangement. However, obviously, I mean, it's a reaction, so we have to have some change. And the change is that so we have no net change in the total number of bonds and types of bonds, but we are going to break 1 sigma bond, and essentially it's going to reappear somewhere else. Obviously, it's not exactly what happens, but it's kind of what it looks like. So it's not a should be a equilibrium arrow. So there's our sigma bond that's broken. And there's our sigma bond that's formed. If it helps you to not think that the molecule is just being flipped over onto its other side, put in like a methyl group there, or something like that. Okay, the mechanism for this looks pretty similar to the Diels-Alder reaction. And when I say pretty similar, I mean like really similar. So we're going to form bond there. You can go clockwise or counterclockwise. I always seem to go clockwise, but your mileage may vary. So everything moves around in a circle, and we end up with this pi bond turning into a sigma bond, so that's our new sigma bond. This pi bond just scoots over, and this sigma bond breaks and becomes a pi bond. So all the carbons still have the same number of hydrogens attached to them. That's a good exercise, would be to draw out all the hydrogens and make sure you can convince yourself of that fact. And we haven't made or formed or broken a ring, notice, right? The starting material here makes it look like a ring because I've drawn where the bond forms, but this is the same molecule and there's no ring here, and there's no ring in the product. So the products and the reactants don't have any rings in them, but the transition state does. So yes.
What did it say before reaction?
Pericyclic. Sorry, that's a C. Pericyclic. Yep. Okay, so there's a little reaction. What does the transition state look like in between? It's good to know what the transition state looks like, but there's another reason that I'm showing you the transition state for this type of reaction specifically. That double dagger just means that there's a transition state, so that's what that is indicating. Okay, so if we look at the bonds that are formed and broken, okay, so what bonds, and here I'm just talking about sigma bonds. This bond is going to go away, and this bond isn't formed, it is formed in the reaction, so it's not there the whole time. So that bond is kind of the transition state is in process when those two things are happening. And so essentially if we get rid of those two bonds that are being made or formed, those two sigma bonds that are being made and formed in the reaction, we've got this 4-carbon fragment at the top and a 3-carbon fragment at the bottom. And that little ring of dots sort of shows the electrons. You can imagine it's sort of another way of showing the mechanism in that the electrons are all moving around in a circle. So if we look at just the number of carbon atoms that are involved in the transition state, for the top fragment there's 3. For the bottom fragment there's also 3. And so we call this a 3-3 sigmatropic rearrangement. Can we see how that transition, the carbons that are drawn out in the transition state correspond to the starting material in the product? Because it looks kind of different, but another exercise you could do is label just 1 through 7, each of the atoms in the starting material in the product, and then correlate that to 1, 2, 3, 4, 5, 6, 7 atoms in the transition state drawing. Might help as well. So most sigmatropic rearrangements are 3-3 sigmatropic rearrangements like you see here and like we're going to talk about right at the end. I do want to make you aware of you don't have to write this down. Of the different kinds that you might see at some point. And that would be a reaction like this, where one of our members of that six-membered transition state, right, we still have that six-membered transition state here. One of the members is a hydrogen. And this is a type of 1,5, because we've got that hydrogen that basically ends up just jumping to the other side of the molecule. And then the whole rest of the transition state is one continuous piece, so that's the 5. So 1,5. Sigmatropic rearrangement. Just to let you know, there's not just 3 3s. As I say that, let's talk about more 3-3 sigmatropic rearrangements. Okay. Okay, so when all of the atoms that are involved in a 3-3 sigmatropic rearrangement are carbon, that might sound like it's the only possible case, it's not. When all of the atoms involved are carbon, it is called a Cope rearrangement after Cope. I don't know who Cope was, but anyway. Let's do, I don't know, that. So, just for funsies, let's do the mechanism. Again, goes in a circle, kind of like the Diels-Alder reaction. So we've got that same arrangement of atoms, but just the bonds have been switched around a little bit. So that's a Cope rearrangement. Okay, kind of standard. This is the same thing that I drew above. It's just got another methyl group to make it interesting. So that's sort of the standard fare of sigmatropic rearrangement. We can replace one of the atoms with an oxygen. And in that case, it's a Claisen rearrangement. By the way, this reaction you get about 85% yield of that product. It's going to be important, kind of. When one atom is an oxygen in that ring of 6 that's participating in the reaction, it's a Claisen. So we can do that. Just replace a carbon with an oxygen. At RT, room temperature, this converts to, let's find out, let's draw the mechanism. Sorry. Okay. Kind of seems like something else might happen, but it's literally the same thing. That bond there, that bond there, and again, just ignore the oxygen and do the same thing. So we'll follow the instructions that the mechanism gives us. That's a double bond, that's a single bond, single bond, single bond, double bond, and this one here is broken. This reaction works even better. It also only goes in one direction. So we go from this ether. This is a vinyl ether because we've got an alkene next to an oxygen. And here we've just got an aldehyde, right? There's a hydrogen there, and so that's an aldehyde. The aldehyde is much more stable, right? Carbon-oxygen double bonds are good, energetically favorable, and so we want to form that carbonyl if possible. Yes?
Could you explain the percentage?
Yes, so the Cope rearrangement, at least in the way it's shown here, is an equilibrium reaction, so it's going back and forth. But when you actually isolate the product, you get 85% actual yield from the theoretical yield just calculated from the molar mass. But when you do this Claisen rearrangement, where you go from an ether to an aldehyde, that's a much more favorable process, and so this isn't really an equilibrium reaction to any significant degree, and you get almost exactly the amount of this product that you would expect based on the stoichiometry, which of course is good because we want as much product as possible.
On the next exam, will
Yes.
you expect to put the percentages?
No. It's just to illustrate how well the reactions work. The final thing is okay, so if we have, no, let me just see our Cope rearrangement. If one atom next to the atoms involved in a Cope rearrangement is an oxygen, then it's called an oxy-Cope. Okay, so how is that different from a Claisen? Well, so that would be just a regular Cope rearrangement, but if we have an ethoxy So like methoxy is 1 carbon, ethoxy is 2 carbons. If we've got an oxygen atom attached to the ring that's involved, or again, ring in quotes, that's involved in the cope rearrangement, that's an oxycope rearrangement. Same thing happens. It's just a slightly different name. I know. Yes, that's it. And these reactions don't work very well because we've generated a vinyl ether, and those aren't particularly stable. But the main thing I want you to be aware of here is that you see the oxygen and you'll go, oh, it's a Claisen rearrangement. Not necessarily. You need to make sure you look at the atoms that are actually involved. In the rearrangement. Okay, so this one at the top here, that's one I gave you previously. Fortunately, we have a little bit of time left that we can mess with that question. And then at the bottom is a rearrangement of some kind. So predict the products and see if you can identify what kind of rearrangement that one at the bottom is. So the top one is Diels-Alder, and the bottom is a rearrangement. Diels-Alder reaction, if it helps you draw out both of the possible products, and then decide which one is more likely to form.
Sorry. I agree.
has this way. So when you look at the top ring, there are no sides to the lines. So I don't know if that's what you're supposed to use that one, but there's also two development pairs. Yeah. So I don't know if it's No, it's not. No, this one is not. Yeah. It's when it's I don't know if we're dealing with it. It's a big issue. Yes, is it just open shape? Okay, if it's the open shape, But he said that this one was just supposed to skip. So then if it's bigger, then this is what I get. You know,
That's what I have like that. You have
this one is turning into this because it is but if it's going to I think it's not really going to it's really it's been my days I'm struggling because
Yeah, so the two double bonds sort of in this ring. And so this ring isn't really the electrons are
that makes sense. Thank you. was just asking you what it is. Yeah, so it's like this. This is the placing.
Okay, for our Diels-Alder reaction, if you draw the resonance structures here, you'll find that this, which from the oxygen upward that's an electron donating group. And so that means that we're going to end up with a partial negative charge on that carbon. And
How do you know it's an EDG?
if you've got an oxygen directly attached to the diene, that's going to be an electron donating group. So an alkoxy group like this, or an alcohol, something like that, those are going to be electron donating. If you've got a carbonyl adjacent, that's going to be an electron withdrawing group. And so if you draw that resonance structure, you'll find a delta plus on that carbon. We want the delta minus and the delta plus to come together as best as possible. And so we should probably reorient our dienophile like that. So just flip it upside down. And that way our delta plus is on the top, and here the delta minus is on the top. And so that tells us the orientation that they're going to react in. So this carbon is that carbon at the very top of the molecule, and so that's going to have the oxygen atom on it. And then the dienophile is here, and the ketone comes off at the bottom. So you could...
If we got the right message, but like we put it on the wrong carbon, would we got like a majority of points or just like some points?
Probably half.
Like, how did you know to flip the?
Flip the dienophile upside down?
Yeah.
Yeah, because we want the delta minus and the delta plus to be close together when the reaction happens.
Okay.
So if our delta minus is at the top here in the diene, we want the delta plus to be at the top in the dienophile.
Okay. Yeah. It's like on mine, I just had the group with no one oxygen, like on the carbon,
Like on this one?
Yeah.
Yeah. So that is the minor product
Okay.
of that reaction.
Oh, so it is correct.
It is a correct answer, but if I'm asking you just for the major product, then it's got to be that one. Okay, then for our sigmatropic rearrangement, we do have two rings in this molecule. Well, we have one ring in the molecule, and then you can kind of see a second ring is kind of implied up here at the top. And that is going to be important for the rearrangement. So we've got a double bond there and a double bond there, and so we can have a sigmatropic rearrangement happening in this top part. So do I want to go clockwise or counterclockwise? It doesn't matter. Any votes? Clockwise. All right, clockwise was first. Okay, well, let me start down here. That's kind of avant-garde, but still correct. So that pi bond goes to there. This pi bond scoots over there. And then this sigma bond, this is the sigma bond that breaks, and it's going to come down there. So to draw the product, okay. If we look at the oxygen, that's going to be a double bond now. So now we have like that. And that's all that's on the oxygen because that sigma bond has broken. So over here, this pi bond has come up to be a sigma bond right there. This pi bond has broken, so this is just a single bond. Then there is a double bond, and then that single bond. Okay, so we still have one ring and one ring, so we haven't had a change in the number of rings, right? And then plus or minus 0 sigma bonds, plus or minus 0 pi bonds. If you count up all the different kinds of bonds, you'll notice there's no change.
Wait, is this one just like sigma?
Sig-
The type of thing we have. What's signature topic?
Sigmatropic rearrangement?
Yeah.
What do you mean?
Is that what this is for?
Yes. So
Is that a one sigma?
that's a comma. Sorry. So this is Diels-Alder. And that's a sigmatropic rearrangement.
Do we have to say like what type of signal?
Isn't it?
What type of sigmatropic rearrangement is it?
Place it?
Yep. Claisen. Okay, so homework for this is going to be due on Tuesday, and then we'll go on to chapter 17, which is about aromatic systems.